Okay, so now let's come back to a system of two systems with angular momenta. So two systems with angular momenta. So the relevant operators are well, obviously J1, which is the, so this one is now the system, not the X component. Okay, so there's J1 and then J2, the angular momentum operators of the second system, J1 squared, J2 squared, etc. Now, we also define a total angular momentum J to be J1 plus J2. So what this really means is that because we now have, a vector space of two particles, H1, 2, which is H1 cross H2, what this really means when we write something like this is that, J1, what it really means is that we are taking J1 acting on the first vector space times the identity operator acting on the second one, okay? And then, similarly, when we write J2, what we are saying is it's, there's an identity operator acting on the first Hilbert space tensored with the identity of a angular momentum operator acting on the second Hilbert space. So this guy will only act on vectors of the first Hilbert space. This guy will only act on vectors on second Hilbert space. Okay? Nahi, do you have a question?
Yes, sir. So the things on the right hand side are represented in the Hilbert space H12, right?
Sorry, can you?
I mean like the same vector J1, the left hand side would say that it's a representation on H1 and the right hand side is on H12. Is that correct?
Oh, this is a notation. I mean, by this I mean this. By this I mean this. This is just a notation.
Oh, okay.
Okay, so this is means that there's an identity operator, which is like I'm not uh, I'm not writing down explicitly. Eta Bangla ujjo. Right. So and then what is J squared? J squared will be J1 squared. Of course, there's an identity operator that I'm not going to write, but just let me write it for now. And then there'll be an identity operator, on the first Hilbert space times J2 squared. And then there'll be a cross term, which will be 2 J1 dotted with J2. And what is this? This is essentially J1 X crossed with J2 X plus J1 Y cross J2Y plus J3Y cross, J3X cross, there should be an X. Oh yeah,
Sir,
sorry, I'm messing things up. Sorry about that. Yeah, this should be Z. Yeah, sorry. This is 3 Z, and then this should be
So 1Z, I think.
1Z. Yeah, sorry. Yeah, I'm getting my 1Z and 2Z. Okay, right. Okay. And because they're acting on different Hilbert spaces, J1, all components of J1 will commute with all components of J2. So what does this mean? This means that J1 crossed with 1 times 1 crossed with J2 minus 1 crossed with J2 times J1 cross with 1 acting on 2. This guy will act on here, so this will just give me J1 cross. This guy will act on here. This will give me J2 minus this guy will act on here. It will give me J1, and this guy will act on here. So this will give me J2, and we see that they're the same, so it's 0. Okay.
Sir, here 1 and 2 represents the Hilbert spaces.
Yeah, exactly. Yeah.
Yeah.
Yeah, exactly. All right. So what is JZ? So JZ is J1Z. Let me not use the brackets. J1Z plus J2Z. I'm going to not write the tensor product anymore. And then J plus minus will be similarly J1 plus minus plus J2 plus minus. Okay? Okay, so these are the operators. So now suppose our two particles or systems are in some state psi 1 and say psi 2, and the only thing that we assume about them, the only thing we assume about them is they have definite total angular, or sorry, not total, definite angular momentum. Definite okay, let me definite values of J1 squared and J2 squared. Okay, given by J1 plus 1 and J2 plus 1. Okay, so what we are saying is that our system, which in state psi 1 has the J angular momentum value J1, and system psi 2, the system 2, which is in state psi 2, has angular momentum J2. So these two are fixed. Okay, we are fixing these two. It can be that some system the same system can have like the J squared value different depending on whether it has absorbed some extra energy, rotational energy from its environment or not. Okay, so and then and suppose that there is some quantum uncertainty in that, then we can say, oh, that system is then in some linear combination of two different total angular J squared angular momentum. We are not assuming things like that. We are assuming that the J1 squared and J2 squared eigenvalues are fixed. Okay, we don't really assume anything else. So the combined system is in a state psi, which is given by the tensor product. So our aim here is to find psi in terms of the eigenkets of Jz. Yeah, sorry. Let me rephrase that. Okay. So our aim is to find the possible size, which are eigenkets of J squared and Jz in terms of the eigenkets of J1z and J2z. Okay, this is what we're going to do. Any questions about what we're going to do?
No, sir.
So I'm going to present the general theory, and I don't think probably I won't be able to get through it today. And if I don't, then I will come back to it in next time. And once we have done the general theory, we'll do a couple of examples, and those couple of examples will make things clearer, hopefully, okay? So this is going to be mathematically a little bit subtle. As you can see from the whole angular momentum business, there's a lot of linear algebra buried here. But, with time, it will become clearer, hopefully.